Okay. Okay, so before we get to where we were last time, I just want to say briefly something you should have noticed. Hopefully, I graded your exams and then created an estimated course grade based on the first three homeworks, the reflections, and the midterm. Of course, there's lots of room to move around, but basically the class is doing pretty well. The midterm itself was went pretty well, I thought. The only slip up I think that was consistent was with Fourier series. And just about everybody did the Fourier series problem. I think maybe only one person didn't. And most people got pretty far along with it. The only thing that I would look at, and this will show up on the final, really had to do. I mean, well, there are two issues. One was just being careful with integration, and that's just a slip up that can happen. Especially when you're integrating by parts and you have to do u substitution, and you can like miss out on n. And if you miss a factor of n in that particular case, odd and even ones cancel or don't cancel. So that could be an issue. The other thing was drawing or sketching the series. There were a number of issues on that. If you look at the solution that I posted for the exam, the main point there was to make sure that you saw that the Fourier series is a continuous series, that it does have that Gibbs phenomena, and then the Dirichlet condition means that at discontinuities, you reach that the solution passes through the midpoint. Okay, those are the main issues. So there'll be another chance at that on the final. The others, they're important, but I won't be asking to do that explicitly. A lot of this builds on early stuff, obviously. But if you have any questions about the exam, please please contact me. And do go over the solutions. I try to be as detailed as possible. Are there any general questions about the midterm? Is it pretty much what you expected? Okay. Well, if you have any issues, please let me know, and I'll be happy to talk to you about that. For today, what we're going to do is go over series solutions. We're going to finish up series solutions so for differential equations. And I've added in at the last minute, which is always a good sign. Let's see how this works. Another example. But what I would say is, I mean, the plan is to go over this method of Frobenius, which is a generalized method, and kind of compare it to the other method that we used. And then on Wednesday, we'll be looking at second solutions and finishing up ordinary differential equations. And you have your next homework is due a week from tomorrow. If you haven't started looking at that, that's okay. Hang on a second. Oh, there's somebody in my backyard, just walking in my backyard. Okay. And on my dock. Okay. All right. Never mind. All right. Weird. Okay. All right. Anyway, so what we're going to do now is look at the Frobenius method. So if you've done the reading, great. If you haven't, also great. The book, as always, is opaque, except with, I think, some examples, and it's encyclopedic. But the idea that I want to impress upon you is that, I mean, where we're headed is what's called the Frobenius method. And you may well be asking yourself, why are we doing another version of the same thing? And that's a valid question. The issue is not all solutions can be represented as, say, y is equal to the sum of a sub n x to the n, right? Where n is some positive power, right? So that was one of the things that, if you go back to last week, on Wednesday, we first introduced the idea of series solutions. We just assume this kind of solution. But there are cases, so for example, if you consider, say, y is equal to cosine of x over x squared, or y is equal to the square root of x times sine of x, neither of these can be represented by a series of non-negative powers, right? Non-negative power series with non-negative powers. So this is where we come in with the Frobenius method and developing what are called indicial equations and recurrence relations. Now, we've already seen recurrence relations, and you've seen that already in other classes. The indicial relations are important because they give us a possible route to something else with second order differential equations. What's the possible benefit for an indicial equation, if you know what an indicial equation is? How many know what an indicial equation is? It's gripping reading, this textbook. Okay, so we're going to find out that an indicial equation automatically gives you the possibility for two solutions. It's by adding an extra root to your power series gives you the possibility, if you remember in your reading, k equals 0 or k equals 1, that gives you two possibilities. It's possible that you can, from just your series solutions, get both linearly independent solutions for a second order differential equation, which is, after all, what we want, right? So the best way to do this is to just jump right in with an example that we've already seen. And kind of, this is really taking a hydrogen bomb to build a gnat, to bomb a gnat, but at least we know what the answer is, right? So if we look at the classical harmonic oscillator problem and ask ourselves, can we create this power series? So I want to make sure I'm at D10. So we know that this is y double prime plus omega squared y, and that's equal to 0. Okay, so nothing hugely weird about that. What we're going to do, and this is what's different from what we've done before, is we're going to let y, the solution to this, be equal to x to the k times the sum over, say, lambda times a sub lambda x to the lambda. Okay. In other words, we're going to multiply x to another power. And so that means that our solution is going to look like lambda equal, the sum from lambda equals 0 to infinity of a sub lambda x to the k plus lambda. And that means y prime is equal to the sum from lambda equals 0 to infinity of a lambda times k plus lambda times x to the k plus lambda minus 1. And y prime is going to be exactly what you'd expect. A sub lambda k plus lambda times k plus lambda minus 1 times x to the k plus lambda minus 2. It's a minus. All right, so that's all D11. All right. Nothing unusual. We're just taking the definition. We're assuming that we can write this solution, or that this solution exists. This guy in my dock is now half in the water. Okay. Just another day in quarantine on the lake. Sorry.
Throw homework at him. He'll never come back.
Well, you know, Arfkin is a good kinetic energy weapon. So, okay, all right. Okay, sorry. So now let's collect all of this. The sum from lambda equals 0 to infinity of a sub lambda k plus lambda times k plus lambda minus 1 times x to the k plus lambda minus 2 plus omega squared times the sum of our original definition, a sub lambda x to the k plus lambda is equal to 0. Well, all right. So the general idea is similar to what we had before. Right? So the general method is to collect terms and make the coefficients vanish, right? The only difference now is that we've got an adjustable parameter k, right? That'll help us write this into what we call an indicial equation. So if we start looking at terms, and again, looking at the same powers of x, we have, in this case, a sub 0 times k minus 1 to the x times x to the k minus 2 for the first term, plus a sub 1 times k plus 1 times k to the minus x times x to the k minus 1. Plus, now that we get to x to the k, we have the value of omega, that is a2 times k plus 2, k plus 1, plus a naught omega squared, x to the k. And so if you notice, what we've done here is that we're just going through each of these series, like in this case, just these two summations. And for lambda equals 0 up here, we get this guy. For lambda equals 1 up here, we get this guy. From lambda equals 0 over here, we get this term, right? So we're just collecting the terms for the different sums, right? So that we can get the same powers of x to that k value. And we can keep going. Say a3k plus 3 times k plus 2 plus a1 omega naught squared times x to the k plus 1, right? If we just match what's going on in each of the sums, then that's going to be equal to 0. Right? Now, clearly, this doesn't do us much good on its own, but now we can look at what each of the coefficients say, right, and set them equal to 0. So, for example, we have from our first term up here, we have a naught times k minus 1 is equal to 0. Right? And from that, we know that k times k minus 1 is equal to 0, or k is equal to 0, or k is equal to 1. And this is what we'll call our indicial equation. In other words, there are going to be two roots to our equation. After we've multiplied x to this arbitrary power, we're trying to find, are there special values of that power? And then does that lead to two different, hopefully linearly independent solutions to this differential equation? Okay, everybody see that? And that's assuming, of course, that a naught is non-zero, right? Which we're trying to assume non-trivial solutions here. So then we can go another term, say a1 times k plus 1 times k is equal to 0. In this case, if k is equal to 1, then we know that a1 is equal to 0. Okay. And we can keep going. A2 times k plus 2 times k plus 1 plus a naught omega squared is equal to 0. And here's where things get a little funky, but funky for a reason. And the notation varies between textbooks. So you'll have to be patient depending on, I know some of you have different editions of ARFCAN. They use different notation. And if you have other textbooks, they'll use different notation too. What we're going to do is let lambda be equal to j plus 2. We're just going to realize, sort of because we know what the answer is already, that there's some benefit to looking at what the coefficient is 2 steps down the line. So that means that we can write the sum from j equals 0 to infinity of a j plus 2 times k plus j plus 2 times k plus j plus 1 x to the k plus j plus omega naught squared times the sum from j equals 0 to infinity of a j x to the k plus j. This is just using our realization that, or the indicial equation that k is going to be equal to 1. The reason why we do this is that we want to be able to look at this. This will be equal to 0. Sorry. Is that we want to compare a sub j2 and a sub j. And we've seen this before in a somewhat different context. When we first talked about Bessel's equation, I think. And what we're trying to do is set up what's called a recurrence relation. Recurrence relations are things that you've seen with, for example, Legendre polynomials, but also we'll see more with the Bessel functions. And so what we're getting is a sub j plus 2 times k plus j plus 2 over, or times k plus j plus 1 plus omega naught squared times aj is equal to 0. In other words, this is i.e. our j plus 2, our j plus second coefficient in this expansion is equal to omega naught squared, whatever that constant is in the problem, times k plus j plus 2 over k plus j plus 1 minus times aj. 14. And I realized that it must be incredibly hard to hear somebody just drone on j, k, 1, 2, lambda, so I apologize. But that's one way of going about getting this recurrence relation. This is our recurrence relation for this problem. If we now consider the case k equals 0, then we have aj plus 2 is equal to minus omega naught squared over j plus 2 times j plus 1 times aj. Okay. So now we're in a position to start using this. So for example, a2 is equal to minus a naught, which is just a constant that's not constrained. So it's going to be whatever it is that we can set will be set by the initial conditions or the boundary conditions of the problem. So a2 is equal to minus a naught times omega naught squared over 2 times 1. right? Because j is equal to 0 on that side. So this is equal to minus omega naught squared over 2 times a naught. A4, you notice that we're setting this up in terms now of even powers, right? Or, well, even powers of x, but even coefficients. So this is equal to minus a2 times omega naught squared over what?
12.
Yes, in other words, 4.3 or omega naught squared 4 factorial times omega naught. A6 would be equal to minus omega naught squared over 6 factorial a naught. And so a sub 2n, so we capture just the even values, is equal to minus 1 to the nth power omega to the 2n over 2n factorial a naught. Oh, yeah. This should be to the 4th. Right. Because what we've done here then is write that y of x for k equals 0 is equal to a naught times 1 minus omega naught x over 2 factorial. Actually, this is squared plus omega naught x to the 4 factorial minus plus, and so on. Or we get a naught times cosine omega naught x. Okay, so what we did was we basically multiplied our series by another power, or x to another power. From that, we looked at what are the two cases. We set up a general recursion relation. Then we considered the one value, one result of that series expansion for one of those values, k0. If we go back to the value for k equals 1, you end up with a sub j2 is equal to minus a j omega naught squared over j plus 3 times j plus 2, and y of x for k equals 1 is a naught sine omega x. Okay, so this is the general form of the Frobenius method. And it's done exactly what we wanted to do. Namely, this is the most general thing that you way of solving differential equation with a power series is if you assume that you can have this multiplier. It works for the general case as well. We'll look at another example in a minute. But the nice thing that this does that the general form doesn't necessarily do for you is it captures both linearly independent solutions, both the cosine and the sine. And so then the general solution would be the addition of the linear combination of both the k equals 0 solution and the k equals 1 solution. Okay. All right, let me pause here. Are there any questions about this or the general method? No. All right, let's see. Make sure I'm doing this right. Let's look at two examples. two additional examples that actually are a little bit more justified than using the simple harmonic oscillator. We're going to return to the Bessel equation. Right. Now, we've seen this before. The idea here, the main thing is eventually when we use Bessel's equation, it's a solution for, or one of the solutions for, say, Laplace's equation in cylindrical coordinates. But we can write this generally as x squared times y double prime plus xy prime plus x squared minus n squared y is equal to 0. So we'll assume a solution from the Frobenius method. So we'll let y of x be a solution that's equal to the sum from lambda equals 0 to infinity of a sub lambda x to the k plus lambda. Okay. All right. So then all we have to do is, if we know what this is, take the second derivative, take the first derivative, be careful of these constants and the fact that we have x's flowing it. In this case, we have x's floating in there with different powers, right? So then we have the sum from lambda equals 0 to infinity of a sub lambda k plus lambda k plus lambda minus 1. This will be your general case when you have something that's multiplied or that starts with a second derivative. And we're going to make sure I've done this correctly. Yep. This is x to the k plus lambda because we've taken 2 powers off x, right, in the differentiation. Plus the sum from lambda equals 0 to infinity of a sub lambda k plus lambda times x to the k plus lambda, plus the sum from lambda equals 0 to infinity of a sub lambda x to the k plus lambda plus 2 minus the sum from lambda equals 0 to infinity of a sub lambda n squared x to the k plus lambda is equal to 0. All right, that's just writing all that crap out. We're going to call this, for future reference, A, this B, this C, and this D, just to keep track of all of these terms. So all we've done is assume a solution that looks like Frobenius and then plugged it all the way through. Right? So our first job, first step after rewriting the differential equation is try and find the indicial equation. And the way you do that is look at the, start looking at the lowest terms. Okay, so we start with the x to the k term. Okay, so in order to do that, let's let lambda be equal to 0 and see what we get. So just looking at the first line in the sum, right? For lambda equals 0, we have a0 times k minus 1 plus k minus n squared equal to 0, again, assuming that a naught is not equal to 0. Okay? That's just looking at sums a, b, c, d, set lambda equal to 0, look at the first terms, and then collect the x to the k, whatever's in front of x to the k. All right. So from this, what do we get in terms of k? What we're after, remember, is trying to solve for our different values, possible values of k. That's our indicial equation.
K equals N.
Right. So in fact, if you go through this, you have k squared minus n squared equals 0. So we have k is equal to plus or minus n, right? Generally speaking, we'll have two possibilities in the indicial equation. And you have a homework question where you're trying to look at the highest root. We call these roots, but I mean, there's solutions for the indicial equation. Okay? Let's go on. We're still with lambda equals 0, and then look at terms for k to the plus 1. Well, we can look at a sub 1 times k plus 1, k plus 1 minus n squared is equal to 0. This is what we do if we have, we set things equal to looking at k, right, the next term in x, and we can rewrite this, rearrange it a little bit, a sub 1 times k plus 1 minus n times k plus 1 plus n equals to 0. But if we use our two known values of n, this is not equal to 0, and this is not equal to 0 for k equal to plus or minus n. So what do we conclude?
A1 is 0.
Right. So our goal here is to set up the differential equation, find the possibilities for k. Generally speaking, we're going to start with the assumption that a naught is not equal to 0, and then see, generally speaking, whether we can, depending on the root, whether we're looking at an odd series or an even series for a solution. All right, so we've now established that a1 is equal to 0, and what we're going to be after is, can we set different subsequent coefficients of a back to a1 so that they're 0, which we did sort of in the first brush with series method. All right, so that in general for k plus j, so some value of j, and we set k equal to n, we consider lambda equal to j. That would be true for a, b, and d, and lambda would be equal to j minus 2 for c. Those are those four sums that I wrote above. Okay, for if we consider a particular value of lambda, then 2 back is because of what we're multiplying or dividing by in that third summation. That means that, oops, let's see, we can write a sub j times n plus j times n plus j minus 1 plus n plus j minus n squared plus a sub j minus 2 is all equal to 0. Or, depending on how you want to write this, a sub j plus 2 is equal to minus 1 over j plus 2 times 2n plus j plus 2 times a sub j. And that would be our recurrence relation for the Bessel equation. So it hasn't, it's set up the solution. It's set up what we can, once we match the differential equations, which once we choose our value of n, so it's a little bit unusual for this case. But it does tell you that if you know one coefficient or one term for the Bessel, a solution of the Bessel equation, you know how to jump ahead 2 spots. Okay. And if you look in your notes, we've hit that before, but in a slightly different way. Another thing that we've seen before, and you've seen before, are Legendre polynomials. So the Legendre equation. So the Legendre polynomials you know, and you know that you can generate the Legendre polynomials if you know what the recurrence relation is. And the point of this last example is to look at how you can get, this is one case where you can get a recurrence relation or general solution using both methods. So the Legendre equation is 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 times y is equal to 0. Okay, so we've seen this before. If you can get away without using Frobenius, it's great, right? So the way that you would do this for without using that method is to go back to what we did last week and consider just a general expansion. That is, assume y is equal to the sum of a sub n x to the n, right? And then what we could do here is line up terms. So we have the constant terms in x, x squared, x cubed, and say x to the L. Actually, n is a bad choice here. Sorry, L. N's a constant, right over here. Okay. If we look at the first derivative or the second derivative of y, we have 2a2, we have 6a3, we have 12a4, we have 20a5, and ultimately L plus 2, L plus 1, AL plus 2. In other words, what we've done is we've taken this form and we've substituted in to all of those, and we started collecting the coefficients in front of each of these different powers of x. So it might actually be best if we look at, go down the line like this, right? So the 0th term would be just going down this way. So there are no constant terms for this expansion. There are no constant terms for this expansion. And the first term in that expansion is n plus times n plus 1 a naught. Does everybody see where we're going? If you don't, raise a hand. Okay, all I've done is take this right here, set L equal to 0, and that gives us 2a2. The other two pieces of that expansion don't have a constant term. And then this last term does. It's just n times n plus 1 times a naught. Everybody with me? All right. Then if we keep this expansion going, for say L equals 1, we have one term that, one coefficient in front of the x. There's no term that depends on x in the second expansion up here. Then we have minus 2a1 here. And we have n times n plus 1 times a1. This is basically doing the same thing that I did when I first showed you power series, with just kind of shifting the sums so that the terms all line up so you can equate the coefficients. We keep going. This is, again, 12 times a sub 4. Now we have minus 2a2. We have minus 4a2. We have n times n plus 1 times a2. That's just going to follow the pattern. And in this last summation, that's going to be the most straightforward, right? It's just the power series times that n times n plus 1. Finally, we have 6a3 minus 6a3, n times n plus 1, a3. And then if we look at the general case, we have minus L times L minus 1 times a sub L over here, minus 2L times a sub L for the third term, and n times n plus 1 times a sub L. In other words, if you follow this through different terms, these are the general expressions for each term. Okay? And we know that each coefficient has to add up to 0 for every power, right, of x. So far, we're just using the general power series solution. Oh, sorry. So we have 2a2 plus n times n plus 1 times a0 is equal to 0. That's just going down this first column. And from that, we get a2 is equal to minus n times n plus 1 over 2 times a naught. Okay. Then if we go down the second column, we get 6a3 plus what do we got here? Oh, I'm expanding this out. N squared minus n minus 2 times a1 is equal to 0, or a3 is equal to minus n minus 1, n plus 2 over 6 times a sub 1. Try to keep the table up there. Go down the third column. We've got collecting terms 12 times a sub 4 plus n squared plus n minus 6 times a2 is equal to 0. So now we have a sub 4 is equal to n times n plus 1 times n minus 2 times n plus 3 all over 4 factorial times a naught. And we could keep going. But what we're after is, for x sub L, we have L plus 2 times L plus 1 times a sub L plus 2 plus n squared plus n minus L squared minus L times a sub L is equal to 0. Or if we keep expanding this, this is L plus 2 times L plus 1 times L a sub L plus 2 plus n minus L times n plus L plus 1 times a sub L is equal to 0. And so a sub L plus 2 is equal to n sub L, times n plus L plus 1 over L plus 2 times L plus 1 times A sub L. So we're lucky in that with this general method, we could find one recurrence relation. We've got one solution, right? That's the problem with this method, is it only gets us the one solution. And that means that y of x then is using this, right? So if we obviously have a common a sub naught. What's the first coefficient, or what's the first value in the series? Okay, I'll give you a hint. We're doing a power expansion, right? So y is equal to the sum of a sub L x to the L.
Is it n times n plus 1?
That's the second term, right? The first term is just 1, right? Because we have to start with a sub 0, right? So we have that. Then we have n times n plus 1. But if this is, we've got basically 2 factorial underneath times x squared plus n times n plus 1 times n minus 2 times n plus 3 over 4 factorial x to the 4th minus plus plus all of that. And we have terms that are multiplied a times a sub 1. And plus 2 over 3 factorial x cubed are odd terms. So this is a mess, understandably a mess, and it's not a closed solution, right? I mean, at least it does give us what the coefficients are for power series expansion, but it's not necessarily obvious, and it's not necessarily something that gives us a quick solution for both linearly independent solutions. Okay. So what can we do? We can try the Frobenius method, right? So what we did before, what we just did was what we did last week. We assumed a simple power series. We did what we could with it. We ended up with this series solution. We should be able to get back to that. But what we want to get is an easy way to find our recurrence relation. So if we use Frobenius, then we have y is equal to the sum from j equals 0 to infinity of a sub j x to j x to the j plus k. Okay. And what's really nice about this is that when you set it up like this, the direct substitution of this gives you almost immediately the recurrence relation. Is a, oops, j plus k times j plus k plus 1 minus n times n plus 1 over j plus k plus 2 times j plus k plus 1 times a sub j, which you might recognize from the first problem set where you used Gauss's convergence criterion for an infinite series. The lowest power of this gives you the indicial equation. So namely, so for the indicial equation, we have the sum of j over j of j plus k times j plus k plus 1 times a sub j x to the j plus k plus or minus 2 minus the sum over j of j plus k times j plus k plus 1 times a sub j x to the j plus k minus 2 times that sum again of j plus k, a sub j x to the j plus k plus n times n plus 1 times the sum of over j of a sub j x to the j k, all equal to 0. If we look at the case when j is equal to 0, right, we have k times k plus 1 times a naught times x to k minus 2 minus k times k plus 1, a naught times x to the k, minus 2k a naught times x to the k, plus n over, or times n plus 1, a naught to the k is equal to 0. Now, if we compare this to what we just did up screen, we know that this has to be equal to 0, and we know that the rest of this has to be equal to 0. And so k times k plus 1 is equal to 0 for a naught not equal to 0, assuming that we have that constant term. And so k is equal to 0 or k is equal to minus 1. This is our indicial equation for the Legendre equation. Okay. And it's from that that we can build up our recursion for the different summation. Namely, we can get a sub j plus 2 is equal to j times j plus 1 minus n times n plus 1 over j plus 2, j plus 1 times aj, which means that a naught's a constant that we determined. We can skip over a1, so we get a2 is equal to n times n plus 1 over 2 times a naught. a4 is equal to 2 times 3 minus n over n plus 1 over 4 times 3 a2, right? Or 3 times 2 times n plus 1 minus n squared over n plus 1 squared over 4 factorial times a naught. We're just jumping back to a naught. Which means that we can boil this down ultimately to minus n times n minus 2 times n plus 1 times n plus 3 over 4 factorial a naught, etc. What point? The point of all of this is to create a series and if the coefficients satisfy those conditions, then it is the solution, right? So we can either use the regular power series or we can use the Frobenius method to get y1 of x, y2 of x. And what we'll do next time is consider the case that we only have one solution. However we got it, how do you get the second solution? And that deals with looking at the creating something called the Wronskian, taking the determinant of that, and then from that, basically creating something that is necessarily both a solution to the differential equation and linearly independent from the solution that you already found. Right? So I know that a lot of this is opaque, but the main idea here, and the questions that I selected for you for your homework are not as complicated as the examples that I did here, I think, maybe the first example. But the questions that you have in the homework really deal with a fairly straightforward expansion, and I'll go over a little bit more of that next time since we're running out of time. But I understand that this is kind of dry and not necessarily straightforward to see. But I would encourage you to take either talk to me or take a differential equation you know the solution to, even a first order differential equation that you know the solution to, and try a series substitution and see if you can create that. Oh, hang on. See if you can create that solution. Looks like I have a meeting, so I'm going to call it here. Are any questions?
Just a real quick question. This
Sure.
might be a dumb question, but
No.
above, what was the direct substitution? I didn't catch what you were substituting where.
Okay, so way up here, I was just
Yeah.
substituting this. I'm pointing at the screen. I'm substituting this into the Legendre equation. So in the first example of that, I just substituted a to the a sub L x to the L, right? And in this example, I'm actually going with the Frobenius substitution so that I can eventually get an indicial equation, right? To see what the two solutions are. Does that make sense? That's why this has J's and K's and N's, and the solution up the page just has the L's and the N's. Make sense?
I think so.
Okay. Take a look at it. I'll post this lecture, and then I'll see if I can come up with another example of this as maybe a little bit more straightforward online. If you would people appreciate another example on Moodle? Okay, I'll do that then. All right, I'll see you guys later. If you have any questions, make sure you talk to me.
Bye, Willow. Bye, Meg.
Bye.
Bye. Thanks.
Let me stop sharing and turn off the video.